Hello everybody, Adam Lusick here, and today we're going to look at training image generation models. Specifically, we're going to be fine-tuning Stable Diffusion XL on two specific downstream tasks. The first one, and here in this example on the left, is going to be on a style transfer. So we're going to take a data set of images all with one style. For this example, it's old book illustrations, fine-tune our Stable Diffusion model, and then all of its subsequent generations are going to then be able to be in that specific style of the data set. The second one is then going to be on what I'm calling more object permanence. So we're going to train it on a data set of a specific object. So for this example here on the right, this was this green chair. And then what that's going to allow us to do is to be able to generate that object in multiple different scenes and maintaining the consistency of the actual object itself. But before we get into the specific details of actually running these training scripts and running these training programs, I think it's quite necessary to go over a lot of the context of how the training actually happens and what's going on behind the scenes so that you can actually understand what's going on during the training process and then be able to later modify this to approach it with your own specific task, with your own specific data set, and then do some of the troubleshooting that comes along with actually training these networks. So if you haven't seen it yet, I have a more generalized video that'll show up right now in the corner that goes over how diffusion models, including image, audio, and video models actually work at a very high level overview. So it doesn't get into any of the real nitty-gritty stuff like what we're going to be going over today. So go ahead and check that out if you haven't to get a good baseline of what's actually happening behind the scenes with diffusion-based models. But assuming you have some familiarity with how diffusion models actually work, then we can get into actually the technical parts of how this happens and how we're going to actually train these. And so the first part is really understanding how Stable Diffusion XL is first set up. And so to kick things off here, it turns out that Stable Diffusion is not actually one overarching model that handles all of the end-to-end process of turning a prompt into an image, but a collection of multiple different machine learning models within it to actually do this full process. So starting from the top with our prompt, we have the positive string and the negative string. The positive string is what we're most familiar with of the actual instructions of what we want the diffusion model to generate. The negative string is an optional argument of where we can explicitly state what we want the model to not generate. And so these strings together are then encoded through two text encoders. Right now, they've been using OpenClip VTG and Clip VT large to do the text encoding. And what they do is they take your string of text and then encode it into a rich representation of the text as an embedding, which is essentially just going to be a large number or string of numbers that will capture the meaning of what your text is. And these models are able to capture the meaning of your text in numbers because they themselves are also machine learning neural network based models. So they take your prompt, convert it into these numbers that contain the meaning of your prompt, and then those are all put together with some Gaussian noise into the latent space. And so the latent space with all of the context of your text encoded prompt is what gets passed to then the base model. And so this is the base unit that is actually going to be doing then the diffusion process of this. And so the base unit is going to take the latent space with the text encoded prompts all together, and then it's going to start the reverse diffusion process of actually generating the image. And so it's going to do that across so many steps up until a point where then those latents, which are quote unquote conditioned because they've been going through the reverse diffusion process already, are passed then to another unit, the refiner model. And the refiner model, similar to the base model, is another diffusion model as well that will take the almost finished conditioned latents that were passed from the base model that did most of the generation and add the final touches in that latent space to create the final representation of our image in latent space, which essentially is just going to be a bunch of numbers. And so all of those numbers then should have some sort of meaning into which we can transform it into a picture. And that's where the VAE decoder comes in. The VAE decoder, which stands for the variational autoencoder, is what's going to take our final conditioned latents that have been passed through the base model, passed through the refiner model, and then turn that actually into the image. So it's going to take that large amount of numbers that are in some sort of array or tensor, or you can think of it as a matrix, and then map those to pixel space. So that's what takes all those numbers and then converts it then into the nice, 1024 by 1024 pixel output image. And so looking at this entire process, it turns out that we are taking advantage of actually 1, 2, 3, 4, 5 specific machine learning models, all within the Stable Diffusion architecture to go from your prompt to an output image. The good part is, though, is that to actually do the training and to do the fine tuning, we only really need to look at the part that's doing the most work, this base model right here. And so that's where all of the information from our prompt, plus the initial noise to kick things off, is then conditioned to do 99% of our generation. And so that here is all that we need to actually attack onto to be able to fine tune for our downstream tasks. It does help, however, to also look at the text encoders. And so what we'll be doing with our specific examples is looking at and specifically tuning this base model, but also the text encoders too as a plus. And so now that we have an idea about how the Stable Diffusion architecture is set up and where we actually need to plug in to affect and fine tune for our specific tasks, let's actually go over what text-to-image model training looks like. And so firstly, if you were wondering why the base model and refiner model here are called a UNet, it is because under the hood, they look like U's here. And this is all the manipulation of the data that's actually going down through here. We're not going to get as specifically deep into what all of this means, but kind of fun to know where the UNet name comes from. So to outline how the text-to-image training process actually happens is the first thing that we're going to be doing, of course, is loading our pre-trained model. And so what we want to do is reuse every component that we can, because obviously the base models like Stable Diffusion and Stable Diffusion Base that they have here are very well made. Took a lot of time, effort, money, and research to put these together. So we don't necessarily want to start from scratch and make our own image model. We want to start with the strong base that Stability AI has been able to give us here and latch onto that. So we'll be loading the base model, as I said. So in their much more simplified diagram here, we can see where the base fits in. And with the base model, we can actually also load both text encoders. And so then, of course, we'll actually need some data to do the fine-tuning process on. And the data will take part in 2 columns. You'll, of course, need an image and then a corresponding prompt that either describes that image or some sort of information about that image. For the dataset about old book illustrations, I have this one prepared right here that has the image, which, for example, we might look at this one here. Lovely old book illustration from what looks like 1914. Great. And then the text here is alt text that I pulled, and it is a woman leans over a tall fish tank and teases the small fish swimming inside with a twig. So we'll take these images and these text corresponding strings and then do a little bit of pre-processing with them as well. In the case of Stable Diffusion XL, what you're going to want to do is first take an original image and then crop it down to the specific resolution of interest. There's many resolutions that Stable Diffusion XL can actually handle, but the most common one is 1024 by 1024 pixels. So in this example of what appears to be a smart young man graduating from UNC, you can see that this original image was then cropped and processed down to 1024 by 1024. Then what happens is the text data, so this prompt that's here, is then tokenized. So it's broken down into different pieces, typically words or subwords, and then each token is transformed into this dense vector embedding that represents the semantic information about the text. So this prompt, a smart young man graduating from UNC, when embedded, then just looks like all of these numbers, but all of those numbers are going to capture the semantic meaning of the prompt here. And the way that it's able to do that is through using this machine learning model. We're going to use the original text encoders that come with the base model when we load it to actually do this pre-processing. Then, of course, we need to get the image in a space where we can kind of shove these together, and that's where the variational autoencoder comes in. So we're going to take this VAE and then encode the image into that latent space abstraction. And this is going to take the image, which right here, and then turn it into what looks like also a bunch of numbers, Turns out in machine learning and neural network, it's all just a bunch of numbers at the end of the day, but the numbers are what mean something. So we take this image, and then this is the numerical representation that's output from the VAE encoding. And so what we're going to do with this data set is we do all of these embeddings as sort of a pre-step. So it's going to go through and create all of those latent space representations of all of these images, and then encode all of the prompts into those embedding spaces as well. And so then once all of the prompts have gone through the encoders and been turned into the embeddings, and then all of our training images have gone through the variational autoencoder and become latent space, then we can do the actual nitty-gritty training of things. You set and load your hyperparameters, which we're going to go into much more detail further, and then do the general training of neural networks. And so this training is a bit of an overview. I go into it, as I mentioned, in much more detail in my prior video that I did, where I break it down with a lot more intuitive steps and images of all of this actually happening. But we're going to do the traditional sample the noise, adding noise to the latent space, sample the time step, sampling a random time step, which helps simulate sort of various stages of adding noise. And then we're going to add the noise to that image input, train the neural network to predict the noise residuals, calculate the loss of the predicted noise versus the actual noise, do all of our backpropagation, and then repeat and validate along the process. And so as that's going on, we can see some of the validation of these in our example, which we're going to get into a little bit later, of actually training on a specific object. But as these weights and biases are being updated and the loss is being calculated, and then all of the internal numbers are being updated, you can see that it'll get closer and closer to our desired output. That's a little bit more consistent with what we're expecting. And so going over this, just loading up some of these validation steps from a different run, you can see how that actually happens over some series of steps. And so the hope is, of course, is that after we've done this entire training process, the network will have learned from our training data to then be able to generalize and replicate what we're teaching it. The thing to note about the process that we just went over is that this is actually the outline for training the entire model itself, which doing that can be a little bit finicky, especially super cost intensive, and requires a lot of GPU compute to actually do all of those things. So what we're going to be doing and going over next is the idea of parameter efficient fine-tuning, specifically with low rank adaptation, or what they call LoRa fine-tuning. And LoRa fine-tuning is a phenomenal way of actually being able to get almost the full effects of completely fine-tuning a model, but only having to fine-tune on very specific parameters. So this will allow you to do it much faster with a lot less compute on a lot less parameters, and still be able to get almost the full effects of fully fine-tuning a model. Additionally, it'll help with a few things like overfitting, which is training your weights very too specifically on the training data that will cause especially diffusion models to just generate one for one your training data. And also the idea of catastrophic forgetting, which is when training these large neural networks, sometimes you can almost overwrite their prior memory or what they've learned already, and they can completely forget large swaths of very necessary information. So by approaching this with LoRa, we'll be able to mitigate a lot of these problems, be able to use less compute, making it more cost effective and more time effective. And the concept of LoRa is not necessarily something that's specifically for diffusion models. It's also used for language models and other different, machine learning models that are generally follow the different transformer architecture. So just to go over the key concept of LoRa so that you can understand what's actually happening behind the scenes and why it is effective before we actually do some, let's go over some of these points. So my overview that I wrote right here is that low rank adaptation is a method designed to sort of adapt large pre-trained models very efficiently by modifying only a small subset of their parameters. And this allows us to be able to fine-tune these models for specific tasks without extensive computational costs associated with sort of traditional methods of training full models, and then also be able to get almost the same output as doing that. And so the core reasons that we use LoRa and the core components of LoRa are as such. The first benefit is the frozen weights of the pre-trained model. So we're actually going to keep all of the prior weights that we have in Stable Diffusion, all here, completely frozen, and not affect them at all during our fine-tuning process. And what we're going to do instead is introduce different trainable low-rank matrices into different layers of the transformer architecture within the Stable Diffusion model. And then these are what's going to be our actual training candidates and what we're going to be running all of our calculations and updating with our fine-tuning data. And these are essentially going to be matrices, and the matrices aren't going to even be sort of the full size and the full complexity of the different matrix that are within the original model, but they're what's called low rank. So low rank is a bit of a mathematical term, but the best way that you can think about it is that they're not as complex semantically. So it's not going to capture the full semantic, embedding or the full sort of understanding of the concepts as similarly or as well as the original model is going to be, but it is very good at generalizing despite being low rank. And all that's to say that we can use sort of smaller, less complex components of the neural network layers to be able to do our best job of approximating sort of our training data and approximating the output that we want. And this is going to be perfectly enough to do exactly what we want to do and get meaningful, reliable, good results at the end without having to do all of the updates and all of the compute for the entire model. So to just summarize this once more real quick into a understandable sentence, instead of training everything, what we're going to do is freeze all of the weights of the original model that we've imported. We're then going to add specific different matrices of weights and biases at different parts in the model, and then those are what's going to become our actual trainable parameters. And then those matrices within that are not as complex and not as large as the regular internal matrices that are doing all of the calculations, but they are large enough to approximate our sort of goal well enough to the point where it's going to make a meaningful difference down the line when we do our training and our fine-tuning. However, this does improve our efficiency and our cost for compute immensely. If you're interested in a little bit of the more specifics of it, LoRa is hyper-focused on actually the attention mechanism within the transformer architecture. So all of the weights and biases that we're adding in our low-rank matrices are going to go on the query, key, value, and the output layers of the self-attention mechanism. The query is what sort of determines how much attention is actually being paid to each element in sort of your input sequence. And then the key is the counterpart to the query that computes the attention scores. The value contains the actual information from the input data that is retrieved after computing the attention. And then the output aggregates all of this into a value matrix to form the output of the attention layer. So this is getting really, really technical and really, really specific, but just know that being able to do this with LoRa, specifically at this part, is what's going to allow us to increase our efficiency and be able to get those meaningful results. Also, in this whole article / guide / blog thing that I've put together, I've got a lot more sort of supporting context and explanations of a few of these things if you're interested in getting deeper into that yourself. So all of this and additional resources will be linked down in the description below, but LoRa simplifies the process of adapting these large-scale models for new tasks by essentially modifying only a fraction of the model's parameters, thus maintaining high efficiency without sacrificing performance. And so our examples and applications for fine-tuning, including the text-to-image example that we just went over before talking about LoRa, and the next one where we're going to be talking about actually maintaining object permanence, will take full advantage of LoRa fine-tuning to be able to do it without needing, thousands of dollars in dedicated GPU clusters or anything like that. And so doing the style transfer part, that's where we're going to be taking advantage of the text-to-image model training approach with also the LoRa application. But to do a little bit more of that object permanence stuff and being able to keep a specific object across multiple scenes, that's where a different methodology, DreamBooth, comes into play. And so the DreamBooth fine-tuning method takes the text-to-image general training method one step further to allow for sort of a specific capability, reliable generation and recreation of specific subjects or objects across multiple scenes. And so a little bit of the key concepts of DreamBooth. DreamBooth was a method from Google Research that takes text-to-image generation that further step by allowing personalized image synthesis with only minimal reference images. So instead of needing a very large data set of maybe, thousands or even billions of images, like how these foundational models are trained, you only need about 3 to 5 images to take advantage of DreamBooth here. And it extends the traditional sort of large-scale text-to-image models, which, while capable of generating very diverse images from text prompts, generally fail to accurately recreate and recontextualize specific subjects or objects. And the way it's able to do this is actually by injecting a unique identifier that sort of corresponds with the input images, your 3 to 5 subjects or your class that you're inputting in. And this unique identifier, one of the more common ones is, these bracketed Vs, or some people say like SKS, which in our example is what we're going to be using. And it's going to be training the text-to-image model with all of this to almost inject this unique identifier and have the model associate it with our small image dataset. To expand on that a little bit more, I break it down a bit here with embedding subjects using unique identifiers in an image text pairing. And so the model is fine-tuned with these text prompts that include that unique identifier, along with a class noun that describes the subject. For example, that might be a token dog, commonly used, as I said, was SKS, V, T0K, some sort of token that's not necessarily present in tokenizers or will be sort of split from the tokenizer into one single token. And so this pair is this pairs the visual features of the subject with the text-based identifier over the training process. And so what we actually want to do is, by training the model on these image text pairs that include the unique identifier, the DreamBooth technique effectively teaches the model to associate these new tokens with the specific visual characteristics of the subject. So then down the line, what we're able to do is, when we're prompting with the fine-tuned DreamBooth model, we can input this unique identifier in, and then the model will associate that with the small training set that we did to be able to recreate said training set across multiple different things. So for their example here, they had these pictures of a dog with the unique identifier of V. Over the training process of the text-to-image training process, this V becomes heavily associated with this dog. And then when you're running the inference or prompting these diffusion models, you might be able to say a V dog in the beach. And then that's where the personalization comes in, where this V is doing a lot of the heavy lifting of the generation, and it ends up associating that with what it learned from these images that you put in of the dog to put him on the beach, or maybe walking on a colorful carpet. One of the more technical ways that they're actually able to do this is through a very special loss function called the class-specific prior preservation loss. And my definition here is that the CSPPL loss function is designed to balance the model's ability to generate the specific subject with its general capability to produce diverse images from the same class. And so it operates by comparing the outputs generated from prompts with and without the unique identifiers, and then it ensures that while the model becomes better and better at actually generating the specific subject, it does not, however, forget how to generate other plausible instances from the same class. So essentially, this will prevent the model from losing its ability to generate other instances of the same thing, such as like a dog, which this issue is called language drift. And also, it will be able to maintain high diversity in its outputs, so it won't be overfitting on the training data as well, and only be able to pretty much recreate exactly the training data. And this loss adjusts the model's training process to ensure that the introduction of the unique identifier doesn't skew the model's overall output or its understanding of the class in any way. To do a bit of a time skip forward, we've already looked at sort of the training overview of the green chair in the prior examples, but if we look at the dataset that we'll be using, which is just this green chair that is around in the current apartment that I'm staying in, we can see then if we go back to our validation training here, we can see that my unique identifier was this bracket V closing bracket. And as it was able to sort of learn from this data set, it gets closer and closer to being able to recreate this chair, but we essentially don't want it to lose the ability to, generate the Grand Canyon. And so we'll go into this with a little bit more detail, but we can see that, maybe it's starting to pick up the floor a little bit too much here, but still it's able to generalize the chair all the way through to the end here. But hopping back over to our explanation of these things, from the DreamBooth paper, some of the different applications that they displayed was recontextualization, generating novel images of specific subjects in different contexts with realistic scene integrations. So a few examples there. Different art renditions of a subject, novel view synthesis of maybe different views of this cat based on only front images of the cat. Property modifications, changing colors or maybe changing breed of a dog, accessorization, outfitting subjects with a variety of accessories, maybe putting this cute dog into a chef outfit. But DreamBooth now really allows us to maintain a subject's likeness during image generation across multiple different applications that we just saw. And so using these tweaks of the text-to-image training method, we can apply this with existing LoRa techniques for subject permanence across scenes during generation. So we'll be focusing primarily on doing the LoRa text-to-image model training for style and DreamBooth for object permanence, but just to give a little bit of an overview of some of the additional methods and ideas and different specific models that are out there, I wanted to include a part about some of those additional methods and ideas. So to go through those quickly, some of the big ideas that I think are interesting are unconditional image generation. So this is training models on a specific data set just to go ahead and run through and start generating. So this isn't being steered by any specific, text or image-based conditions where you might input an image to start or input a prompt that's encoded similar to Stable Diffusion. This is just going to start generating random stuff. There's also some things that are very similar to DreamBooth as well. There's textual inversion, which takes sort of the same idea, but what it does is it introduces the new words into the embedding space of the pre-trained text-to-image model, and then does sort of very similar stuff to what DreamBooth did to be able to sort of maintain the ideas behind a small data set. There's custom diffusion, which takes sort of the idea with this to a bit of an efficiency landscape, where what it'll do is it'll grab a bunch of similar pictures for the training process to enable super fast training of different user-defined concepts like personal items, pets, or family members by grabbing similar objects or similar images to what was input and used to bolster the training and make it quicker. Some other fun things is people have actually developed reinforcement learning with diffusion models. So instead of just doing the traditional optimizations with a loss function, they've implemented ways to use vision models to somehow score and then do reinforcement learning. There's also a whole bunch of other ways of preconditioning image models, which essentially preconditioning might mean putting in something like line art or what's called like a canny guided edge or a sketch or this depth representation or even a pose into a text to image model and then having it generate on top of that with the guidance of that. And one of these things here is this text to image adapters module that can plug on top of different text to image models, remaining unchanged, but allow them to take in these different guides to more specifically guide the model into some sort of different outcome. Some other cool ideas is latent consistency distillation, which is essentially making it so that instead of 50 or 100 steps that you need to actually generate an image, it can be done with just 2 to 4 steps. And then also some other ideas of actually doing that preconditioning and putting in sort of different maps of what you want before doing the generation to get a desired output. And all sorts of other stuff that I've outlined here in much greater detail. One of these catches your eye, please check out this guide and check out the different websites for all of these and the different papers where all of these are implemented. Sweet. So that pretty much sums up all of the different methodology and the theories and the ideas behind it. Of course, the best way to understand a lot of these is actually applying them yourself and putting them into practice. And we'll be doing this with a little bit of guidance here right now. And so the first thing that I wanted to highlight is an easy package that we're going to use to both do the training, the inference, and the loading of a lot of these models, and that is the HuggingFace Diffusers package. And the HuggingFace Diffusers package, if we go to their main landing page, is what they say the go-to library for state-of-the-art pre-trained diffusion models for generating all sorts of stuff, whether you want inference solutions or training your own. This is a really nice package that makes it super easy to both load, use, and train models. The library itself has sort of three main components. They have pipelines, which are a super easy way to actually run the diffusion models and load them and sort of automatically grab all of the different components needed so that when you load something like, Stable Diffusion base, it'll also grab the VAE, it'll grab both of the text encoders and everything else you need to actually make sure that this runs and put it all together. It also has different schedulers, which are functions for the diffusion process itself. The scheduler is what takes sort of the model's output, the sample which the diffusion process is iterating on, and a timestamp to return a denoise sample. This is crucial for the actual reverse diffusion process, and I won't get into too much detail about the scheduler since that's not really what we're looking at here, but that's the second part. And then the third part is that they just have all sorts of integrations with existing pre-trained models and popular algorithms and stuff for diffusion models that you can take, use, mix, match, put together, all to sort of develop, research, and test out the whole diffusion process yourself. On top of allowing easy testing and interfacing and loading of these models, they also have a bunch of pre-made scripts and all sorts of good stuff for actually training diffusion models. So we're going to be taking advantage of this and breaking down the scripts and running some of them and showing what that looks like to actually apply what we've gone over for DreamBooth and text-to-image model training ourselves. And so if you go into the Diffusers GitHub repo, they actually have a whole bunch of examples of different training scripts. And so if you scroll down to text to image, you can see a whole README of Stable Diffusion XL, text to image fine tuning. And then more specifically, if you look at it, you've got this big, huge script that will take care of almost the entire process of training and uploading your trained model for you. And similarly enough, also, they've got plenty of things for DreamBooth and then, custom diffusion, control net, all that stuff that we went over, but a good README of the training example with DreamBooth. And then, of course, they have a nice long script to automate this process for you as well. But the one issue I found is that, well, it does give you a good starting point of actually showing how to run these scripts and the different, parameters or what that might look like when you're running it on a GPU setup. It doesn't actually tell you sort of good information about every single possibility that you can add into your script here. So what I've done is I've gone through and I've read through pretty much both of these entire scripts to document exactly what the arguments are, a little bit of what they mean, and what they might affect when you're setting up sort of your environment and setting up a script to do this type of training. Obviously, there are a lot of arguments, and I was mostly surprised that they didn't have, something fully like this that listed out every single possible argument here, at least readily available from what I understood from getting to know this process and understand this. But no worries, it was a phenomenal learning opportunity to list out every single argument and all that it does. So obviously, I'm not going to go through line by line and tell you all what each one of these does, but we're going to go over some of the scripts that I actually used myself and how I set them up and break down those a little bit more specifically. However, you should know that within this resource that I'll have linked down below, you can see all of the different scripts, the different conditions that it takes, and more detailed descriptions than what's actually in the code itself of what all of these do and how they might affect your training process. So this top one here is for the text-to-image SDXL LoRa training script, which goes over all of these. And then what I did for the DreamBooth script is that they share a lot of the same arguments. So all that I did was actually show the differences between this one, the DreamBooth script, and then the prior one. And so these are all of the new arguments. Of course, the one thing to note here is that the instance prompt is very specific. That's where you'll be adding in that unique identifier, and then also the removed arguments of what is no longer in this script. So that's just all of these. So if you want to know and set up your own hyperparameters and everything, this will be a great way to look over, understand a little bit about what's going on at each one of these, and then be able to tune your own training to exactly what you would like. But I don't want to bore you with going over every single one of those arguments, so those are there for your reference and hopefully should provide a little bit more context of how you can set up your own. But what I do have now are two examples of scripts that I actually successfully ran and that will be using the trained models and the trained adapters a little bit later on. So I'm actually going to break down these now and show you exactly what each one of these does in this script. So without further ado, this is what the entire script and actually setting it up, running that training file, and then passing in the arguments looks like. Let's break it down a little bit line by line to show exactly why I put these things there and what they mean. So breakdown of the arguments, I have the pre-trained model name or path. That of course is going to path directly to Stability AI, Stable Diffusion XL base. That is of course our base model that we want to load that we'll be doing the fine tuning on. Then we have also a specific variational autoencoder model name or path. And what someone here, this made by Allen individual, has lovingly made is a fixed variational autoencoder that helps actually with the training process and is modified to run in floating point 16 precision. So that's phenomenal. It's just a quick fix of the VAE that helps a lot with some of the generations and with our lower precision training that we've got here. So then, of course, you have to path to the dataset name, and that is going to be my old books illustration small dataset, which is publicly available right here for anyone to use and contains just images and the corresponding text. Then, of course, you need a validation prompt. And so this is what is going to happen during training. You can validate in steps using some sort of logging process to evaluate how well the model can actually generate the images based on the given textual description at the various stages of training. This is, of course, exactly what we were doing here with our example of the green chair, but it needs a prompt to kick that off. And so I just thought up one that was an inventor tinkers with a complex machine in his workshop, oblivious to the setting sun outside. And so that's all fun and all. Then you can specify the number of validation images that you want to be generated. So I have 4. That's why right here with validation, it's 4 specific images. Useful to see because, if it just printed out this one, I might be like, wow, it's not doing well at all. But if it just printed out this one, I'd be like, okay, it's, doing very decently. It's picked up on this and maybe a little bit too much of the floor there. And then validation epochs. And this is how many times it's actually going to run a validation. And an epoch is essentially one sort of pass through the training data. So once it's gone through the entire training data once, that is an epoch. So I have it go through and run a validation after every single epoch. The output directory will just specify where you want to save all of the files that are being generated. The resolution is what you're going to set for the actual validation images and the resolution of the training. This will actually cut your images into this resolution if need be, if it's not the right resolution already. So we did some pre-processing and I showed a little bit of pre-processing of actually setting your resolution to 1024, but this script will handle that and actually resize your images regardless if you specify a value here. And then also center crop is if it does need to be cropped into this specific resolution, it'll just crop from the center. Random flip, it will apply random horizontal flips to the training images that can help with a little bit more of that training and generalization so that it doesn't just see the same image over and over. It'll randomly flip a few, which will change how it's actually being processed. Then a few fun things here is that we're going to be training the text encoder as well. And this is a cool option that the script allows, which allows us to take the text encoders, the clip models that are taking our prompts, and then embedding them into the latent space for our model. And we can additionally train our text encoder part there. And then there's a few more hyperparameters here that you can say, and these are actually getting into a lot of the processing power that you might be on. So you can do the train batch size, which is which specifies how many images per device you're training on in steps. And so smaller batch sizes can reduce memory usage, but may slow down the training process. If you are GPU rich and have a lot of RAM, you can increase the batch size, but it is generally very difficult to train large scale image models, so I kept this down pretty low. The number of training epochs is how many epochs we actually want to process and do the training for. I set this one to 10, so it'll pass through the entire dataset 10 times. You can also specify whether or not you want to save checkpoints of the model. So you can actually load from different points in the training, and I have it save a checkpoint every 500 steps here. Gradient accumulation steps is going to sort of simulate batch size without actually having to use batch size. It's going to accumulate some of the calculations that are being ran over multiple steps before running and doing all of the updates. And so that'll help stabilize the training and also help with being a little bit more memory efficient. One of the most important things that we've got here is the learning rate. The learning rate controls how much to adjust the actual model's weights with respect to this calculated loss gradient. Smaller rate can lead to more stable but slower convergence. You can do a few things with the learning rate, and I have it have no warm-up steps, so it'll start right at 1e negative 4, which is going to be 0.0001, but you can actually have it warm up to prevent updates in sort of the early stages of training. I have it report to weights and biases, which is what we're looking at here, to actually be able to track and see some of the training metrics when it's running. Then I have the data loader number workers as 8, and that uses 8 subprocesses for loading the data. So it'll load all of our dataset images and dataset stuff a little bit more effectively. We're going to allow TF32, which is TensorFloat 32, which is very specifically geared towards Ampere architecture GPUs. I was training on an A100, which takes advantage of the Ampere GPU architecture, so I allowed this. You can then also do mixed precision. So FP16 means that it uses 16-bit floating point precision for training, which will reduce a lot of the memory usage and can speed up training on the compatible hardware. Then a few things here, integrations with HuggingFace. We've got push to hub, which will upload my model to the HuggingFace hub, and then the hub model ID to do that. And that was a mouthful, but I have a little bit of descriptions for each one of these too. So if you want to go through and look at what each one of these are doing, and then also, of course, as I mentioned, all of the arguments in a lot more in a lot more context here up at the top if you want to put together something similar. However, this is the exact script that I was actually able to use to make my model, the SDXL Base 1.0 Old Book Illustrations LoRa adapters. And to save you all from having me ramble off line by line every single thing again, I also have an example of the DreamBooth script, but I'm not going to explain each one of these as a lot of these are redundant, but some of the things here that are different is the inclusion of the instance prompt. And this is where you're going to put in that unique identifier plus a noun. So I put in a photo of SKS chair. You could put in just SKS chair. This might be where you put in like the bracketed V with dog, something like that. And then the rest of it follows a pretty similar layout to what we just went over with this one. And then of course you can mix and match, add and take off for your own individual use case. With all of that explanation out of the way, feel free to reuse the script that I use and use some of the information that I put down in this resource to modify it and test things out to make it exactly to your liking and suitable for your different conditions, your data set, and your training environment. But With that being said, let's actually give an example of running a script and seeing what that looks like when connected to a GPU environment and doing the training. So what I've got down here is a list of just different options that you can do to snag a cloud GPU. Here's some of the spots that just Googling around, this is what came up for me. You know, if any of these are seeing this and want to sponsor me with some compute, feel free to reach out. Would be more than happy to do that. But here are some of the options. What I've got up here are the ones that are a little bit easier for individual users to use, and they allow you to sort of rent GPUs pretty easily with some easy integrations to stuff like, you know, Jupyter notebooks or command line interfaces right off the bat. Or you can take advantage of a lot of your more popular cloud platforms like GCP, AWS, or Azure and whatnot. But what I actually did is both of the scripts that I used were trained on an A100 with 40 gigabytes of VRAM. And there are a lot of downfalls to that. The A100s are generally a little bit more pricey to rent, somewhere between $1 or $2 per hour. And you might want to do that with a little bit less. So I have some ideas here and some additional actual arguments that you can put in if you don't want to spend the money, spend the time to rent a very powerful GPU, and maybe you have like some sort of consumer grade card like a RTX 30 series or an RTX 40 series lying around that you could take advantage of. However, we're going to look at actually just running up one of these A100s and kicking off a script. So no free clout, but I'm connected now to a cloud GPU, and we are looking at an NVIDIA A100 XSM 40 gigabyte with about 40 gigabytes of VRAM. And so once you've connected to sort of your preferred environment and have a GPU up and running, this might also be your own personal computer or something like that doing this processing. These are kind of the steps that you can take to actually get things kicked off. So of course, what we're going to need to do is clone the Diffusers library. We're going to cd, change the directory, Diffusers into that, and then install all of the dependencies here. Cool. That's doing it all well. And then we'll go into where our training script is going to be, and then we can install the requirements from the requirements tab. Then what you're going to want to do is log into HuggingFace. And so that will bring up this. And then you're going to have to input your HuggingFace token. And so I just did that there. And then if you want to track stuff, you need to install weights and biases or sort of your preferred tracking service. I just use weights and biases. It's pretty easy. And then you can just run 1b login, and then similar to what I had, you log in with your API key, which I have a direct link to here. The fourth step is configuring Accelerate, and Accelerate is actually the package that sort of helps run PyTorch code across GPUs. So it's another Hugging Face package. Not going to go into this one in detail in this video, but it will help run all of this on GPUs all nicely. So you can just pass in accelerate config, and if you have a config of your own, you can pass that there, or you can just say default. So I just set it up with the default one. And then a few things that I actually know from trying this out a few times is that there's a few additional things that I need to install. So this might vary for you, and this is a good time to talk about when you're running these things. A lot of the times your first time running the script won't actually go too well. It's going to probably throw up some sort of error, you probably have some sort of, packages need to be upgraded, or you might need to install some dependencies that aren't there. Just read what error it's throwing when you're trying to run these scripts, and then do all of that, as need be. But I know for a fact that I needed to upgrade Pillow and install a different version of NumPy from doing this a little bit before. And then the easy thing is that you can actually just copy this all over, set it up, and it should work perfectly. So it's going to have to go through and actually do a lot of downloading the model and downloading the dataset and getting things running. But if we give this just a second here, we'll see that it'll go through. Right now it's downloading all of the files that we actually need from HuggingFace. So it'll be loading in like Stable Diffusion base and the additional fixed variational autoencoder and doing all of that fun stuff. And I'll let this run, hop back here in a second. Sweet, so now it's actually downloaded the full model, and now it's downloading the dataset. So the training part should actually be coming up real soon now. Here we go. Logging into weights and biases, and then great, we can see that we've got 1,000 examples running on 10 epochs, instantaneous batch size of 1, accumulation steps. It's going to be a total of 2,500 steps, and it looks like it's going to be about 3 hours. So now we've got this nice bar here that we can track it. If we go over to our HuggingFace, we can see that it's automatically created this model card here, and this is where everything is going to be uploaded at the end. And then if we go over to weights and biases here, we can see that because we're logged in, we can start to see all of this start training. So that's how you would set this up and run them. And as a side note, tuning all of these hyperparameters and choosing all of the things that you actually put here, even down to like the validation prompt and all of these different numbers, is nothing short of actually an art form. So tinker around with a lot of this stuff, see what works for you, see what outputs you're getting, definitely monitor the progress as you're looking around with your preferred monitoring system, and best of luck actually training these. It takes a lot of time, but it's really rewarding once you get them going, and that's what we'll be going into next, the actual outcomes of some of these models that I've trained. Awesome. So I've gone through and I've done a few iterations of these trainings on a few different things, and I've put together now 2 of the models that I was teasing here at the beginning. The base old books illustration one, the regular text to image fine tuning, and then one for DreamBooth fine tuning that's specifically on this green chair. So let's actually load these up in some collab notebooks and generate some images. So now we've hopped over to this first collab notebook to show the example of our results from tuning on old book illustrations. So actually loading this is super duper easy. We can use the same diffusion pipeline class from the Diffusers package to automatically load everything that we need from our base model. So we just set this pipeline up as from pre-trained, path over to Stable Diffusion base, pass in a few more arguments here that you can look into. One of the things that I did was enable CPU offloading so that when we're not actually generating, it can offload a lot of the work to the CPU. And then loading our LoRa weights here is as simple as copying this path, heading over, and then just using the load LoRa weights method. And so I've done that. And now what we can do is generate an image. So invoking that pipe, you can pass in a prompt, pass in the number of inference steps, the different height, width, and a little bit of the guidance scale, which will essentially show how much, or which will guide the model towards being more in line with your prompt rather than generating other things. You can think of it a little bit like the temperature of a language model. That's a little bit of what the guidance scale actually helps with, but just invoking this base model, we can get an image, and hopefully this image will show a man laying out in a grassy field looking up at the clouds, but in the style, oh, there you go, in the style of an old book illustration. So maybe it's got some work to do of actually showing the man itself, but let's try something a little bit different here. let's say, a big Ferris wheel. So yeah, this looks perfect. This is exactly what I would expect from being trained on old book illustrations. And instead of just popping out a big Ferris wheel, it does it in the style of old book illustrations. So that's great to see, and our training worked. Loading up the DreamBooth tuned model is also very similar to exactly what we just did with loading the base model and then loading the LoRa weights here. While this is loading and downloading everything, I did want to talk a little bit about the finicky part of DreamBooth models. And still, as you can see, I've trained about 5 or 6 different variations to try and get this a little bit more perfect. But one of the things with my data set is that each one of these images of the green chair also includes a lot of the same similarities. So you'll see that this actually down here, these ones all have the same like black background, and then even more so, they all have the same cement floor. So one of the things that I was trying to see is the balance between not picking up the cement floor, but still being able to generate the chair well. And we can see that maybe I needed a little bit more of a diverse data set. But at the end of the day, and sometimes even like this one, it'll start to generate a lot of the data set that I don't want. So DreamBooth can be a little bit more finicky if you're not doing it with, some super specialized and tuned up parameters, but you can still get some pretty decent results. Although I believe my model might have picked up a little bit too much also on the floor of the chair, not just the chair. But let's give it a shot and see what we've got. So the biggest thing is that now we have this identifier, which my identifier is a photo of SKS chair. And so that identifier is what you're going to want to include with the rest of your prompt to sort of have the language model actually generate an image and use what it's learned from your data set with the unique identifier to try and put that into a new scene. So let's try and do it in the middle of a snowy tundra with trees. Great. So we can see that it actually picked up pretty well the chair, and then it chose to do it facing this way. But we can see that contrary to the cement of my apartment, the chair is now in a snowy wasteland. So that's pretty cool. It's able to do this. I would say it's a little bit more finicky than the general style transfer, but given that it's on a much smaller data set and ran for a much smaller amount of steps, being able to do this is still really cool. Great, so we can see that both fine tunes on general style transfer with text to image, and then also our DreamBooth attempt was able to do pretty well and give us some decent results. So, of course, this resource that has all of these how-tos and all of the different breakdowns of everything is going to be available for you to use in the description below. And all of my models that I've shown and displayed in this video are available on just my HuggingFace account. They are directly linked here, along with the collab notebooks that will allow you to actually run them. So feel free to try out the models. You can also use my datasets if you'd like to try and train your own kind of things. Give it a shot, and best of luck with training. That being said, I hope that a lot of this was some helpful context into the methodology and then also a little bit of the technicalities of running these training scripts and understanding what's happening when you're fine-tuning diffusion models on something like style or on teaching it to recognize and regenerate an object. If you enjoyed it, drop a like. If you like these videos and want to see more, hit that subscribe. And if you've got any questions, feel free to leave them down in the comments. Thank you and have a good day.